Okay, so let me introduce the speaker first. In this week, we are very glad to have Charlotte Chang from the MIT to give us today's talk. And her title is Flag Varieties and Representations of the p-adic groups. Yeah, Charlotte, please.
Thank you very much for the invitation, and also to the audience for attending. So this is my title, and so this talk is based on joint work with Alexander Ivanov and also joint work with Masao Oi. And so Masao, this talk is not directed to you. You are an expert on this topic. But so what so let me just start with some historical remarks. So historically, geometry has played a huge role in representation theory, and so this can mean a variety of fancy things, arbitrarily fancy things in some sense. But for me, I would think that I think of like the most classical interpretation of so-called geometric representation theory is the idea that one can find interesting representations inside the cohomology of interesting varieties. And so so let me say give some just examples, most of which will not come up again later in the talk. For Borel-Weybot realizes the algebraic representations of complex semi-simple Lie groups in the coherent cohomology of a flag variety. Springer fibers give you representations of Sn. The Leustic varieties, which we will see later in the talk, see the irreducible representations of finite groups of Lie type. Shimura varieties have actions by adelic groups, and so there are representations there. And Stukas know about groups over function fields. And what I want to give a picture of today is the role of representation, the role of geometry in the representation theory of p-adic groups and the relation to the Langlands program. So some slice of this story. And a lot of this story is, as we'll see, is kind of developing in recent years. So it's certainly not the complete story. Okay, so what I'd like to do is start by introducing Leustic theory. And so in Leustic theory, what we're concerned about is representations of G of FQ, where G is a connected reductive group. So these are things like GLN FQ or SLN FQ or symplectic group of FQ, exceptional groups, this kind of thing. And so in the beginning, I mean, like if you ask, oh, what is the representation theory of X, where X is some large class of groups, like you do some examples first. And so in the 50s and the 60s, it was calculated by hand in some sense what the character tables were for GLN FQ and also symplectic group. And based on these character tables, MacDonald conjectured that essentially the irreducible representations of this finite group of Lie type, this G of FQ, should be parametrized by irreducible representations of maximal tori. So the idea being that the stuff on this left-hand side here, is easy, and the stuff on this right-hand side is something harder. I mean, tori are abelian, so they have easy representation theory. And so there's some part of this correspondence that's attainable in an elementary way. And this is the setting of when your maximal torus is what's called, and these correspond to what are called principal series representations of G of FQ. And what this means is that these representations arise from parabolic induction from a Borel subgroup. And so let me give you an example of what this looks like for a very small group. So if I take SL2 FQ, then an example of a split torus sitting inside here is the torus given by this diagonal thing. So of course I've determinant 1, and so this diagonal is isomorphic to FQ cross, FQ star. And this diagonal is contained inside this Borel here. And moreover, there's a surjection from this B to this torus here. Right. So what this means is that given any character of here, I can always pull back along this surjection and view it as a character of B. And so what this means then is, so I put this theta in here, I view it as a character of B, and I do this algebraic construction where I just induce from B to SL2FQ. And so this is principal series. Okay. Okay, so I should also say I got really excited and jumped into the talk without saying some other words that I had planned on saying. But so if at any point during the talk you would like me to slow down or give a specific example, please speak up. You can also type things in chat. I do have it. I will try to look whether things come up in the chat. Yeah. Okay. So I also I can only judge from the facial expressions of those with videos on. So if you would also like, if your facial expressions would also like to be taken into consideration, please turn your video on. Okay, so here are two related facts. The first is that these principal series representations aren't all the irreducible representations. And the second thing is that there are non-split maximal tori inside G of FQ. And so what does this mean? Well, let me give you an example. So let's go back to SL2FQ. So previously I had this example where the torus was just this diagonal thing. But there's another torus inside here as well. And this can be, and one way to view this is if instead of thinking of this, I mean, I can think of this FQ squared as a true dimensional vector space over FQ. And then this group here, the kernel of the norm map from FQ star to FQ star sits inside this SL2 here. And now this thing one can calculate is has order q plus 1. It's isomorphic to mu q plus 1. And this is a torus. And okay, so maybe it's not so clear what it means to be a torus, but what one could think about is if you base change this situation to FQ squared even, then this kind of object will be the kernel from some like FQ, like something like FQ squared cross FQ squared cross. Oh, this is like not the way to write. Okay, something like FQ squared cross FQ squared cross to FQ squared cross. And then this will give you an FQ squared cross. And so it's like, it looks like a GM when you base change to FQ squared. So this is in the sense in which this is a torus. And so under this recipe where I'm going from characters of tori to irreducibles of my G of FQ, this sends characters of mu q plus 1 to what are called cuspidal representations of SL2FQ. And how I want to think about them, about these cuspidal representations of SL2FQ, are these are the ones that do not come up in principal series. So basically we have this dichotomy where SL2 has a split torus and a non-split torus. The split tori give rise to principal series representations, and the non-split ones give rise to the cuspidal representations. Okay. So in 1974, through work in another direction, work on what Drinfeld called elliptic modules, which we now call Drinfeld modules, Drinfeld proved and knew that the cohomology of this curve right here realizes the cuspidal representations of SL2FQ. And so what exactly does that mean? Well, this curve right here has contains an action of this group and an action of this group, and these two actions commute. So I wrote down explicitly what this recipe is so SL2 acts on X by just matrix multiplication on XY, and mu Q plus 1 acts on XY by just scaling. So what homothety, right? So okay. So because these two actions commute with each other, this means that when I look at the cohomology of this object, I get a representation of this group cross this group. So each cohomology group is a QL bar vector space that has an action of this and an action of this commuting actions. And so what that means is I can break up this cohomology by whatever this mu Q plus 1 is doing, the easy group, break up this cohomology by the action of the easy group. So if I'm given some theta, a character of mu Q plus 1, I'm going to let this notation denote the subspace of the cohomology where mu Q plus 1 acts by multiplication by theta. Yeah. Okay. And then because I've now isolated the way that mu Q plus 1 acts, this will be a representation of SL2FQ. So this a rep of SL2FQ. Okay. And so that's where this recipe is now. This map that goes from irreducible representations of mu Q plus 1 to cuspidal reps of SL2FQ is given by sending theta to the theta isotypic component of this cohomology. Okay. So this picture, in fact, generalizes. And so motivated by Drinfeld's example for SL2, Deligne and Leustic wrote down how to do this in general. That is, if I start with, okay, we're gonna have some notational things. Okay, if I start with a torus, it says T here, but later I call this S, so I'm gonna call all these to S. And yeah, okay. If I have a maximal torus S inside my connected reductive group G, and I choose some Borel that contains this, now this Borel might not be defined over this FQ, but it's at least defined over FQ bar, but you just select this, and I mean, this is not so important. It turns out that this story does not depend on the choice of this Borel, so don't worry about this too much, but I need it so that I can define the Linguistic variety. So what they defined is a variety that is kind of a sub-variety of a flag variety, even though it doesn't really look like it here. And it is given by this recipe. So it's the set of things inside the algebraic group G such that X inverse sigma of X is inside the unipotent radical of my chosen Borel. Okay, so this is some very nice variety over FQ bar. And the thing to observe about this is, like the Drinfeld curve, I have an action by my G of FQ by left multiplication, because if I multiply on the left here, this inverse means that it spits it out over here, but G of FQ is the same as G of FQ bar sigma fixed points, and so it'll cancel out in the middle. And then we have an action by this S over here because S normalizes the unipotent. So what this means is I can do the same recipe as before. Given a character of a maximal torus, I can attach to this a representation of G of FQ by looking at the cohomology and the part of the cohomology where my torus is acting by a particular specified character theta. Okay. And the theorem of Deligne-Leustic says the following, that every irreducible of G of FQ appears in this cohomology somewhere, and secondly, if this theta is in so-called in general position, and this will be something that comes up later, but essentially in general position, you should think of it as being like far away from the trivial representation. If theta is in general position, then this cohomology group right here, this is irreducible and also concentrated in the middle degree. Questions? So in other words, what this theorem is saying is that this map star here resolves Macdonald's conjecture in some way, where it says there's some in general position locus of the irreducibles of this finite reductive group of Lie type, where those representations are genuinely parametrized by in general position characters of maximal tori. Okay, so this is a chart, and what I just explained now is the role of these people in this box here. And so in fact, there is no known algebraic construction of these representations. You can do it in special cases, but there's no uniform way to do it for all of the all irreducibles of all groups of this in this class. So that's a comment. And so for the rest of our talk, what I will do is slowly fill out this chart. And so this will be our guiding post for where we are in the story. And so what I will do next is just very briefly say something about this box to get some number theory in right now. Okay. Any questions? Okay. So I think maybe the most famous object in this box are Shimura varieties, and they're famous for a variety of reasons. And in the local picture, they're famous for their role in the local Langlands correspondence. And so there's a related object called the Lubin-Tate Tower. And in the 90s, Deline and Carayol conjectured that the local Langlands correspondence for GLN is realized inside the cohomology of this Lubin-Tate Tower, whatever this object is. And so over some years, there were some very big results establishing this in different cases. But one thing that over the last couple of decades, people have found they want to understand better is, if we know that the local Langlands correspondence is realized in this thing, can we see somehow more explicitly that what is happening on a representation theoretic level? And moreover, as far as I understand, these proofs up here require some kind of Shimura variety input, which means that it involves something like embedding a local field inside a global field that has it at its place. But the local Langlands correspondence is a purely local statement. So in some sense, there should be a purely local reason that the cohomology of this local object realizes this correspondence. And so this spurred a lot of work. And I think the first time we the first known study of special aphanoids in this Lubin-Tate Tower is by Yoshida, who found that these X0, that is these Deline Leustic varieties for GLN FQ, appear inside this Lubin-Tate Tower. And so this is maybe one way to think of, you could think of this as being like a local explanation for why you get depth 0 supercuspitals inside this cohomology. And so since then, there have been works by many other people as well, finding special aphanoids in the Lubin-Tate Tower, but that reduce to some finite type variety over FQ bar that kind of look like Deline Leustic varieties, but aren't exactly Deline Leustic varieties. Okay. Okay. So that's our new input right here. This blue. Okay. So the structure of what I'd like to do next is I will explain something about what happens here. Then I will explain something about what happens here. And then I will explain something about how these two are related. And if time permits, I will explain something about how these two are related, at least in a special case. Okay, so why is there something here? Well, people have known for some time how to construct at least some supercuspidal representations of p-adic groups. And this is done in an algebraic way. And so let me begin by giving you the simplest possible recipe of such things. Which is the following. So I'm going to have F throughout for this and for the rest of the talk as well. This big F will be a non-Archimedean local field with residue field FQ, and OF will be the ring of integers. Oh, and also either this or this is the uniformizer. I forget what I used. So in the case of SL2, the way to build what's called the depth zero supercuspidal is to first start with this Drinfeld curve. So I start with this Drinfeld curve, and I look at some theta eigenspace inside this cohomology. This is an irreducible and cuspidal representation of SL2 FQ. And then what I can do is that because SL2OF surjects onto SL2FQ, I can pull back this representation to a representation of SL2FQ. And then once I have this representation of SL2FQ, I'm just going to take the compact induction from the SL2OF to SL2 of F. Okay, so it's a three-part step. So this is some geometric input, this is just pulling back, and this is just induction. Okay, so, well, there's also been, I mean, since starting in the 60s or 70s and continuing on to now, we also know how to construct at least some positive depth supercuspidals. And here's the generic recipe for this, and I'll show how to modify this simple recipe to get a more general thing, which is, okay, so I now cross out depth zero and I put positive depth. Positive depth supercuspidals come from still sticking this step one here, keeping this the same, but now instead of this very easy thing of just pulling back the representation, I'm going to replace this by some complicated recipe. And this complicated algebraic construction is, you could think of it as that's the thing that's giving it positive depth. So the algebraic part is this positive part. And then I keep step three the same. And so this, as I mentioned, has a long history. Corwin and Howe studied constructions of this type for GLN and inner forms of GLN. Girardin studied a more maybe general G, maybe not completely general G, but relatively general G, and constructed a class of positive depth supercuspidals. And then there was a major breakthrough by Adler, who constructed who gave a new idea that then later influenced you to give what we now have as the most general construction of supercuspidals. Okay, so essentially, what I will talk about is like in these two things, I really mean use construction, keeping in mind that it was influenced by a lot of previous work. Okay, so let me give some comments about use construction in a special case. And this special case will be the case of so-called regular supercuspidal representations. This is terminology by Tasho Khalifa. So in general, use construction builds a supercuspidal out of a lot of data. And this data, I mean, there's 5 things in the, I mean, some of it is a little bit redundant, but the point here is that it takes in, like, for instance, you specify a sequence of so-called twisted levy subgroups, characters of those levies. These are essentially how deep these characters are. This is a point in the building, and this is a depth 0 thing. So this row 0 is the row 0 that we've seen before, this thing that comes from the cohomology of linguistic varieties. But it's also, I mean, it's not the case that 2 distinct quintuples of this type will give rise to different supercuspidals. So Hakim and Murnaghan give an explicit description of when 2 such quintuples give rise to the same supercuspidal. And what Tasho found is that there's a kind of regular locus of these objects where this quintuple of data is actually can be characterized by a much simpler collection of data. That data just being an elliptic maximal torus with some other adjectives and a character of it. So this looks okay, yeah. So what we see, in other words, is that because these Hakim-Murnaghan equivalence classes of these quintuples correspond to supercuspidals, and regular supercuspidals, because we're only looking inside this regular locus, then composing this and this gives me a one-to-one correspondence between objects of this type and objects of this type, which now makes this p-adic picture look a lot like the finite fields picture, right? Where we had McDonald's conjecture, where a certain regular locus of irreducible representations of G of FQ are parameterized by regular characters of maximal tori. Okay, and so what we've seen so far is that from Deligne-Leustic theory, I can build with some algebraic input a representation of this G of X0, which in our example was SL2 of OF. And from this, I can do a compact induction to get to a representation of the p-adic group. Okay. I'll pause and maybe give people a chance to ask a question if they would like to. Okay. So we now have this recipe for going up here. And now I will say something about what could go inside this box here. Okay. So my setup from this discussion of regular representations is that I'm trying to get a representation of a p-adic group from the data of a maximal torus and a character of that maximal torus. And so that's my starting input in this here, where I'm trying to construct a representation of G of a GX0 and parahoric. And from this data, this in fact corresponds to, I mean, this uniquely determines a parahoric subgroup GX0, which if you haven't seen parahoric subgroups before, you could think of this as a kind of integral version of a parabolic. So for instance, if I look inside GLN FQ and I take a parabolic subgroup, so that's something that's like block upper triangular, and now I look at the surjection from GLN FQ, GLN OF to GLN FQ, I can look at the pre-image of this block upper triangular thing inside GLN OF, and that resulting object is called a parahoric. There are more general things as well, but this is the flavor of what we're working with. And an important feature of these GX zeros is that this 0 can change to other numbers. So the X will always be there. But so this GX0 comes with a kind of filtration of congruent subgroups called Moy-Prasad filtration. And this assigns to every non-negative real number a subgroup GXR of this GX0. And let me give you an example of what this looks like. So if I take this, if I take SL2F and I start with a GX0 that looks like SL2OF, then GXR will just be all matrices that look like the identity modulo sum, like the rth power of your uniformizer. Okay. And so what that means is that when I take the quotient of GX0 by something like GXR or GXR plus, I will get SL2 of some quotient ring, some finite quotient ring. Okay. Okay, so here is the definition of a Leustic variety for a parahoric subgroup. And there's a bunch of symbols here, but the way you should think about this is the definition for classical Leustic varieties, except that I beefed everything up. So what do I mean by that? Well, if I look over here, if I set R to be equal to 0, this then just recovers for me SL2FQ. And so this is kind of like adding more like more variables in some sense. I can think of it as kind of like like truncated polynomials or something in one variable. Okay. So I have this bunch of symbols here, but the main thing here is that I again have this situation where I can left multiply by the sigma fixed points and right multiply by something that looks like a torus. And so that's this S0 quotient by SR plus here. It's something that plays the role of a torus, even though you wouldn't literally call it a torus in this situation. And this definition for essentially the more or less arbitrary parahoric subgroups is a generalization of a definition studied by Leustic in the equal characteristic case and Stasinski in the mixed characteristic case. What they did was essentially the hyper special case. I mean, something actually a little bit more special than hyper special, but and so let me state the main theorem of why we want this object. So the main theorem is that if I take this theta and it's generic in some way, so this Torah is a genericity condition. This in general position is the same kind of condition as in the finite field case. And this depth R is just so that I know which R to put over here. If I take a theta that's very generic, so very, very far away from the trivial representation, then this eigenspace is an irreducible representation of GX0. Okay. So in other words, I can start with the data of S and theta and get a representation of GX0, an irreducible representation of GX0 from this geometric object. And secondly, what I know is that there's on the points in here that come from regular semi-simple points, the character formula of this representation is extremely easy. It's just an averaging over this theta. Okay. So this averaging over this theta, this formula will come up later. So just think, just remember, it's good when the character just looks like an average over theta, over translates of theta.
Charlotte, could I interrupt with a question?
Yes, yes.
This XR, you're thinking of it as variety over the residual field, right?
Yes, over FQ bar. Yeah.
Okay. Thank you.
Yeah. Thank you. Yeah. So so when R equals 0, then this will exactly be a Deligne-Leustic variety. And as R grows, this variety will grow in dimension. But this variety is still like smooth and separated and affine, finite type, all basically like the desirable adjectives that you'd want on a variety.
So the representation in the atom 1, the part 1, the cohomology representation for the GX0, it is trivial on the R plus. It is the factors through the GX R plus.
That's right. That's right. Yep.
And do you know what Leustic did?
Yes.
I guess in Covalis, he has an article where is that where he considered these varieties? And
yeah, so I will talk about the Corvallis article at the end. That will be in this box actually. This was a later paper. Actually, this was a 2004 paper where he didn't consider the p-adic group at all. He just considered groups of this form.
Okay. I see. Okay. Thank you.
Okay, so what we've seen here is filling out of this square here. Okay, so what we don't know yet, I mean, there are several things we don't know yet, but maybe what I would like to say next is, I mean, okay, so because of the way I've set up this chart, I hope that this is motivated to be a very natural thing to fill in, but it turns out that there's another natural reason to want something here. And so in order to explain that, I will talk about L packets as studied from this perspective, this algebraic perspective. Okay, so I want to say some words about L packets of toral supercuspidal representations. And so, I mean, I won't be able to say, okay, so what are L packets? Very vaguely speaking, is these are some finite sets of supercuspidal representations which should have some nice properties associated to them. So for example, maybe you'd want the central character to be the same for all elements inside the packet, or you'd want the formal degree to be constant on the packet. And the property that I'd like to focus on is the notion of stability, that L packets should be stable. So let me explain what this word stable is about. So in general, when you say stable conjugacy class, this means that not only are you allowing conjugation by elements inside G of F, but also elements inside G of F bar, which where F bar is a chosen algebraic closure of F. And so we say that if I have a function, just any function, a G of F to C, we say that this function is stable if it's constant on stable conjugacy classes. Okay. So right, so from like representation theory 101, we know that the trace is stable on conjugacy classes, but it may not be the case that it's stable on stable conjugacy classes. Okay, and so we say that if I have a finite set of supercuspidals pi 1 through pi n, this is going to be stable if some, okay, if essentially the average over the characters is stable. And if my pi 1 through pi n are regular supercuspidals, like what we saw before this, then what we saw before is that regular supercuspidals correspond to just this data of a pair of a maximal torus and a character of that maximal torus. And so this each pi I will correspond to an SI and a character theta I. Okay. And so what's natural now is to ask whether there's just an intrinsic notion of stability on the side of S comma theta, and there is. We say a stable conjugacy class of this S comma theta is, I mean, it's like a conjugacy classes of these things, except you're allowed to conjugate by things in G of F bar. Okay. And so what I have now is that regular supercuspidals correspond to these kinds of things. We want an L packet of regular supercuspidals, which then correspond to these S theta. A natural thing to expect is that if I start with a stable conjugacy class of S theta and I map them all to the to supercuspidals of G of F, then I will get a stable set of regular supercuspidals. So I've just repeated the guess at the top here. And so let me tell you the two special classes of regular supercuspidals. The first special class are what we've already seen, depth zero representations. This was the first recipe of supercuspidals that we saw, where we started with the Leustic representation. But that Leustic representation, remember, that came from an S comma theta. And then we did this process where we pulled back to the integral level, and then took the induction to the p-adic group. And so in this situation, it's, I mean, pretty clear what this theta to pi theta should be, because we know what the finite field recipe from characters of Torah to irreducibles of the group give us. And so it turns out that this guess is true in the depth zero setting. And this was proved by independently by De Backer, Rieder, and also Kazhdan, Warshawski. Okay, so that's the simplest possible class of regular supercuspidals. The next simplest possible class of regular supercuspidals are positive depth, and they're toral. So we see this word toral come up again. So this is again, this is some genericity condition, and it's saying it's very, very far from being trivial. And in this situation, this pi theta was actually already considered by Adler. This was Adler's breakthrough that I talked about in the previous one of the previous slides. And instead of taking something algebraic, geometric, this is a purely algebraic object here. There's some construction for a rho theta, some irreducible representation of this parahoric here, and then I compactly induce this thing. It turns out to be irreducible and therefore supercuspidal. And in this situation, it turns out that this guess that this map theta to pi theta should preserve stability, this is not true. And so this was studied by Rieder, who proved stability of formal degree, and Rieder had conjectured that it was true, that this recipe theta to pi theta would preserve stability, but this was later seen to be not the case by De Backer and Spice. But De Backer Spice also not only proved that it didn't work, but also fixed the issue. And the issue is a normalization issue, essentially, which is that you need to twist by a quadratic character in order to get a correspondence that is stable. Okay, so that's what works here means. Okay, so now we have a bunch of different representations of GX0 floating around, right? We have this, oh, I guess I should put this rho theta. We have this rho theta that we saw right here. We have this rho xi theta, which is this De Backer Spice twist. And we also have this geometrically arising guy, cohomology of XR. So we have these objects in this picture, and the natural question to ask now is what is the relationship between this geometrically constructed representation with this algebraically constructed representation? And so this is the question that Masao Oi and I are trying to understand. And here is the theorem in the Torah situation. There's a bit of a caveat with small q that I won't say too much about, but you can ask me about. So the theorem is that if theta is toral in general position and has depth r, then this representation, this induced representation where I feed in only the geometric guy, the cohomology of xr, this is irreducible supercuspidal, and it's isomorphic to the twisted one, the twisted p-adic representation. Okay. But the consequence now is that we know that if I get the twisted one, then the recipe that goes from, I guess, s comma theta to this this compact induction, this does preserve stability, right? So this is a consequence. Just, you know, we know it because the algebraic side knew it, and now we can compare geometric side to algebraic side, and therefore this gives a geometric realization of these alpaca. Then it doesn't. I mean, you don't have to know what the construction is. You could just say it as it is the cohomology of this xr, which of course is mysterious in another way and simple in another way. Okay. So now there's a question of right, like if you're given two representations, how can you possibly compare two representations to each other, right? And one way, of course, is to try to compare one. I mean, explicitly map one construction to the other construction. But in general, the use construction is not so easy, and the cohomology is not so easy, and so this kind of explicit way is pretty hard in general. And I should mention here that there's a special case where an explicit comparison between Girardin's construction and a special case of these XRs has been done. This has been done by Zhe Chen and Alexander Stasinski under some conditions, like R has to be even, and this XR, I mean, this XR is associated to a pair that looks like G of you know, like boldface G of OF or something like this. Okay. And so our strategy is a little bit different. Is that instead of comparing the two constructions, we compare the end result. So, and our strategy is inspired by work of Enyart, who thought about GLN and inner forms of GLN in the 90s. And the idea is that if I am given a sufficiently generic irreducible representation, this representation is determined by its character on a kind of small part of the group. So in other words, you don't need to know the character at every single conjugacy class to determine the entire representation. And the part we need is the regular semi-simple locus. But we're lucky because it's exactly on this regular semi-simple locus that we have this easy character formula. So once again, we see this thing where we have the trace of some representation being the averaging over the orbit of the original character that we started with. But note here that I now already have this twist xi inside the subscript of rho here. Okay. So what we prove is that this rho theta is characterized, maybe I should put a rho xi theta here, is characterized by its character on the regular locus, on a kind of regular locus of gx0. And more precisely, the statement is that if I am given an irreducible representation of pi, in fact, you don't have to know that it's an irreducible representation of pi, because we want to apply this to cohomology. Cohomology, I mean, we're taking the alternating sum of cohomology groups. So it might not literally be a representation, it might be minus a representation. And so we want to let that flexibility go in here as well. So when I say irreducible virtual representation, I mean that either pi is irreducible or minus pi is irreducible. So if I have an irreducible virtual representation pi, such that there is some constant and some character theta, sufficiently generic theta, where the trace of this irreducible pi is equal to this averaging up to this constant c, then I know some things. First, I know that the c must be equal to this sign that came up over here, and that c times pi is the genuine representation. So in other words, this factor out here is actually picking up some kind of cohomological information. It's picking up a parity. And moreover, this pi, I should put a c pi here. C times pi is isomorphic to rho xi theta as representations of gx0. And so what we see here is that because of this previous theorem, in my joint work with Alex Ivanov, where we calculate some basic properties of what these geometric representations look like, and because of theorem 3, this comparison theorem now just becomes an application of theorem 3 to the particular situation where I take pi to be this alternating sum of cohomology groups. And an advantage here also is that this theorem gives you a way of comparing different constructions as well, not just this geometric one. If you have some other construction that seems to, that you expect to get the supercuspidals, you can try to look at what the character is at regular semisimple points. And if it looks like this, then this theorem will tell you that it's kind of pinpointed. You have to have had this representation that came from you. And this was actually the way that that Enyart used his GLN results, which is that in the 80s and 70s and 80s, there were lots of different constructions of supercuspidals of GLN QP, GLN F, and it was very difficult to compare them because they might have, their constructions are often extremely different in nature. But it was easy, at least, to calculate the character on this kind of regular locus. Okay.
That's a quick question,
so,
Charlotte.
Yeah.
In theorem 2, this rho sub zeta theta, so that this is a representation of gx0 or the gf.
Yes, of gx0. Yeah.
The gx0. Okay, so you are doing the comparison of characters for the
yes.
Thank you.
Yeah. It would be great if we could do it for just representations of the p-adic group on the get-go, but we don't know how to do this as yet.
But on the other hand, regular supercuspitals, right? So Tascio has character formulas for the supercuspital at the end on S0 regular. So there must be some consistency between the two. Or not?
Yes, there is consistency between the two. So this toral setting is a special case of Kalitha's setting. And so in Kalitha's setting, I mean, he has some a conjecture for what the L package should look like. And what he does is he defines this kind of twisting xi for regular supercuspidals as well. And this is ongoing work that we have and so far what we see is that even outside the toral setting, if you make some assumption on the irreducibility of this one, which we don't know right now, you also get a matching with Kalitha's twisting. And this twisting here is the twisting of de Backer-Spice, which is a special case of Kalitha's twisting.
Yeah, but so in Theorem 2, like, I mean, what's the, do you prove Theorem 2 using Carletta's character formula, or I mean, does one imply the other? I mean,
so,
for example.
No, so this is a kind of similar to Carletta's character formula, except we genuinely need to do some work here too, because I mean, first we're doing it at this level, and the existing character formulas are not in terms of this this kind of average. And so we need to sort out a bunch of terms in order to change the indexing set to be what matches the geometric side, what arises naturally on the geometric side. And then in this construction, we do use construction. We use like, we look at use construction. Use construction says do the following process, and using a variety of tricks, basically, and with clever applications of Frobenius reciprocity and things like, if I know something is true on the regular part, then I can do some kind of telescoping series to prove that some other Helm space is non-zero, and that's what gives us Theorem 3. So it's for Theorem 3, it's not enough to know what the character is. We need to know something about what the representation looks like. Yeah, so so what we have up to here now is that I have my my depth 0, 1 over here that we started with. Then we got this rho theta, which compactly induces to this pi theta. And then we discussed this this geometric construction, and this geometric construction is related to this rho theta via this twist xi, which was exactly the twist that we needed in order to get preservation of stability. Okay, so in the last, just I'll take maybe around 5 more minutes. So Lei told me that I could take up to 2 hours, which is dangerous. But so I will take another 5 minutes, and then what I want to say is something about this return to this square here, which is that in this lower row of this picture here, what we see is that Leustic appears here and here, but not yet here. So what I will do here is now talk about Leustic's contribution to this box. And so we take, again, this Deligne-Leustic type of construction that we saw in the finite field case, that we saw in the parahoric case, and now we put it in the p-adic setting. And okay, so there's an extra quotient here, and that's basically because these are now infinite level, infinite, like very infinite things, and maybe one has to worry about whether you're bigger by an affine space of infinite dimension. But in any case, this is the definition of a so-called loop Deligne-Leustic set. And so this terminology is not native to Leustic, but it's kind of loop in some way, but because the idea is that we want to try to understand this set as an object over FQ bar. And so that's the sense in which this is loop. So right, and so this is the set that that Leustic introduced in the Corvallis proceedings. So your question we took before about whether this middle part was what Leustic had done in the Corvallis proceedings. Yeah, so this is his Leustic's conjecture. It's a very short paper in the Corvallis proceedings, like maybe 4 pages, very influential. Okay, so like all the previous Deligne-Leustic type of constructions, we have a left action by the sigma fixed points of the group and a right action by something by a torus. And what Leustic conjectured in this paper in 79 is that this object here, which a priori doesn't have an algebrogeometric structure, basically because it's so infinite, it should have some kind of algebrogeometric structure, that very likely of some infinite dimensional thing, but that's okay. And moreover, one should be able to define some homology groups of this infinitely, this very infinite object, such that when I feed in a smooth character, the theta isotypic part of the homology group should give me a smooth representation of G of F, because that's the category that everything is, for me, is in. And secondly, is that if theta is in general position, then this homology group should be an irreducible supercuspidal representation. So I should put a star here because we want to kind of look at all the eyes all at once. Okay. So actually, very recent work of my collaborator Ivanov, he has shown that there's a functor that is at least representable by an int scheme. So and this solves part of the first solves part of the first part of this conjecture, which is that if I take a Coxeter torus S, then there is at least this X is an int scheme. Okay, but it's not yet known how to define these homology groups. And because it's not yet known how to define the homology groups, it's not known what representations are in the homology. But there's a special case. There's a special case when it is known how to define the homology groups. And I will now end the talk with a bit about that. So I've repeated Leustic's conjecture here in slightly smaller scale. So in the setting that my p-adic group is an inner form of GLN, this elliptic torus S here is just isomorphic to E star, where E is a degree n unramified extension of F. And in this case, we can study this loop Deligne-Leustic set quite explicitly. And what Alex and I found, what Ivanov and I found, was first, by studying it explicitly, we found that this, if you look at the connected components of this, it looks like this variety here. So in other words, this X basically just puts all of these XRs together into one massive object. And what we also did was we defined a family of affine Deligne-Leustic varieties, which are certain sub-varieties of affine flag varieties cut out by Deligne-Leustic-like conditions, things like, X inverse sigma X has to be somewhere, or X inverse B sigma X has to be somewhere. And we could define these homology groups essentially by using this middle object right here. So these XRs. So, and then once you have this, then the homology, the study of what representations arise in the homology of X reduces to a question of what representations arise in the cohomology of XR. And so the second part of Leustic's conjecture, in this special case that G is an inner form of GLN, holds for theta in general position in this setting. And so in a slightly special case, so not super special case is what I mean, Alex and I gave a geometric approach to this problem where we study irreducibility from a geometric perspective. And in fact, this theorem with Masao Oi, our comparison leads to Y. Okay, I don't know what leads to Y means, but this comparison also yields the second part of Leustic's conjecture in the special case that G is an inner form of GLN. Okay, okay. So in this special case, I just want to mention that because we know that our torus is just this E star, where E is a degree and unramified field extension, this theta we say is this notion of in general position just means that theta has trivial stabilizer inside the Galois group. And on the number theory side, I mean, this is exactly the kind of condition you expect to have if you're going to get an n-dimensional irreducible representation of the corresponding Bay group from a character theta. So there's some consistency here. Okay. And in the special case, even more special case that G is the division algebra, this is the setting where we know the most. We essentially know everything about these the cohomology of these various geometric objects. And so, for instance, we also know that these homology groups, these theta isotypic parts of these homology groups, are concentrated in a single degree. And that comes from the calculation that the cohomology of XR is concentrated in a single degree. But now we actually have a departure from what happens in the depth zero setting. So in the reductive groups, in the finite field setting. In that setting, remember we had if you had a theta in general position, then the corresponding cohomology would be concentrated in a single degree, and it had to be in the middle degree, right? But that's not the case here. The case here is that you can have a regular character that's in general position, and it will appear somewhere like between the middle and the top degree. And essentially the way to think about it is like it's in the middle degree in the most generic situation, and as you move slightly away from that most generic situation towards the trivial character, you will move up in the cohomology, but you will still be concentrated in a single degree. And right now it doesn't seem possible. Those methods just do not work for these other XRs. So this is really the situation where we know the most information. And I'll stop there. Thanks very much. Oh, so this is the last slide. Yeah, thank you.
Thank you. Okay, any question?
Can I ask a question?
Yes.
Is there some modular interpretation of the Affine-Deligne-Leustic variety construct? For example, you use this Affine-Deligne-Leustic infinite level Affine-Deligne-Leustic varieties to construct certain local llamas. Is it related to some kind of modular space of let's say p-divisible group with some level structure?
Yeah. So the tricky thing here in this in making this work is that we construct a bunch of, I mean, there's a bunch of indices, but basically, I mean, Affine-Deligne-Leustic varieties care about, I mean, they're dictated by two parameters, a W and a B, but we also have an R, and this thing will sit inside something that looks like G mod the Arth the Arth congruent subgroup of the Iwahori. And in order to define this Affine-Deligne-Leustic variety at infinite level, we need to find maps between these Affine-Deligne-Leustic varieties. So while it is the case that each of these likely has a moduli interpretation because this side does, so you know it's some subvariety of that thing, we tried for some time to understand what the maps between these varieties were from the moduli interpretation, and we can't do it. So yeah, this is a little bit misleading because this really relied on choosing these Affine-Deligne-Leustic varieties in a very particular way so that there are tons and tons of maps between them, whereas in general you don't really expect to have nice maps between random Affine-Deligne-Leustic varieties.
Okay.
Hey, Charlotte.
Yes, Xu
May I first add some remarks to this question about this modular interpretation?
Oh, yes, please. Yes, please.
And yes, I remember that actually I talked to Tom Hens several years ago. And so he was actually trying to understand about the affine Linguistic variety for the positive level and for the modular interpretation. And I don't remember the details because actually the work actually has not actually been written down yet after several years. But what he actually told me is that if you actually look at actually even the smallest positive levels, then you actually have to use a stack language. I mean, for the modular interpretation, and the things become extremely difficult.
I see.
And you may actually contact him to see if there's any updates.
Yeah. I see.
Yeah, and also actually, may
I see. Yeah.
May I also ask you about the last line? You say that this actually does not occur in the middle degree.
Yeah. Mm-hmm.
And so it's actually because that the XI in general is not affine, is not affine variety.
No, XI is affine. Yeah, XI is affine.
Okay.
And so because it's affine, then its compactly supportive cohomology has to lie between the middle and the top, right?
Okay.
And it can appear anywhere there, and genuinely does. And so the idea basically is that there's something called the Howe factorization, which says that if I'm given a theta of from E to C star, then I can write theta as a product of let me make sure. Yeah, I can write it like this. F n I over no, the other way. E over F n I times and a bunch of things. F, let's say K, norm E over F n K, where this is constructed so that each of these theta i's is minimal in the sense that you can't write it as this kind of composition. Like it doesn't factor through an additional norm map. And so if you're in the situation where there's only one term in this factorization, then it occurs in the middle degree.
Okay.
Sorry. Wait. Right. So if there's only one term in this factorization and you're also in general position, then that means that you didn't factor through any norm, like in the most general way possible. And so in that situation, then you're in the middle degree. But it is also possible to not factor through the norm, but be written in this way. I think maybe you also need the condition that the depth of these characters is decreasing or something like that. So how I think of it is that I have my OE has like pi squared, etc. And at some point, all my characters are smooth, so I can truncate at some point. So right before it becomes trivial, I ask, does that thing on this very last piece where now it's just like a additive character of FQN, does that have trivial stabilizer under the Galois group? If it does have trivial Galois group stabilizer, then that means that this corresponds to the so-called Torah setting. And in this situation, it's concentrated in the middle degree. But now you could like multiply such a thing by something that's deeper but factorizes through a norm map. And in this situation, you will be shifted a little bit. And in fact, I mean, like I wrote down an exact formula for which cohomological degree you landed. So it's very explicit in terms of this how factorization.
I see. Thank you. May I actually ask another question?
Yes.
Okay, so is this actually your construction with Ivanov also works if you actually think about the Chevalier groups over finite rings?
Yes.
And do you actually get to the classifications of the irreducibles in that way, or? Wait,
what's the Chevalier group over a finite
for
ring?
example, if you think about the GLM of the FQ X quotient out by X cube.
FQ X
quotient out by X cube.
X cube. Oh, I see. Yes. Yeah, we do. Yes. And then your question is what?
And I mean, if you actually study this, actually, is it possible to get to the classification of the irreducibles for these finite groups?
Oh, so I think George wrote this down for SL2 FQ quotient X, FQX quotient by X to the 4.
Yes. He actually told me that. I mean, if you quotient by the outer degree, then this is actually extremely difficult.
Right.
He actually studied for quotient by to the evens power.
Yeah. So there's this even odd thing that happens, and my expectation for why there's an even odd thing that happens is that there's also an even odd thing that happens in use construction.
Okay.
And I think that these things are related, which is that in one of the two situations, you can the recipe for the supercuspidal doesn't involve the Weil representation.
Mm-hmm.
And in the other parity, you do need the Weil representation to extend the representation a little bit more in order to make the induced thing actually irreducible. And so this to me fits in, like, you know, just like pattern matching. And so that's what I expect, is that because there's the Weil representation comes up, it makes things harder. And of course, use representation isn't about constructing all the representations of this Chevalier group over a finite ring. So but maybe it gives a glimpse into why, like, that already for the ones that you need for supercuspidals, you already have this odd is harder than even situation.
I see. Okay, thank you.
Okay. So any other questions?
Oh, sorry. Can I ask one more question?
Yes.
So how do we understand this twisting character? You need to twist the correct character on the Torah from the point of view of geometry. Why do you have to do this?
Oh, you mean why is it that the geometry sees this?
Right.
Yeah, I mean, the geometry has no idea about it. What?
Yeah, because when you have this construction, you do not need to. So you do not see this, let's say, rectifying character or something. You cannot see it.
Right. So the geometry doesn't know about use correspondence from theta to pi theta. It only knows about theta to pi xi theta.
Is that intrinsic, which means that this has already been contained in the let's say geometric
yeah,
construction.
yeah, like somehow something in the geometry is already forcing it to have this twist. And I guess one way to think about it is, I mean, because the U parameterization on the nose is not stable, one might think, okay, well, the geometry knows about the stability. You know, the geometry knows about the stability, and so that's why it automatically sees the xi in there already. But I mean, like, if your question is just looking at the geometric part, how do I, like, can I write down or recover this xi in some natural way from the geometry? I think the answer is no. It just so happened that xi is the thing that you need to twist from one construction to the other. But I don't know, Masao, if you have a better answer, then please speak up.
Okay, thanks.
Yeah, thanks for the question.
Okay, so any other questions? Okay, if you have no question, let's thanks Charles the beautiful talk. Yes, thank you.
Thank you.